Okay, without further ado then, let's get started. I have two items from graph theory that I wanted to discuss and three items from group theory, and then one item at the intersection. Yeah, so general, the setup for today is I'll talk a bit about the types of um, things you might want to use from Maple if you are teaching a group theory or graph theory course. Um, and Yeah, what sorts of things like visualization and the like you might want to do. Um, so let's get started with graph theory. I'll start by loading the graph theory package. And I also loaded the sub package. Special graphs, we'll use that. Actually, we won't use that in the first section, but we'll use that when we talk about colorings. So if we one subject that will typically come up in graph theory is max flow, min cut type problems, right? I mean, there's sort of broadly two types of things you talk about in graph theory. There's um, the study of graphs um, uh, as as just individual objects of study, and what can we say about their properties and their theory and whatever that sort of thing. And then there is sort of using graphs in all sorts of applications. And I took one example of sort of both streams. The max flow problem is, of course, something that you use in application type situations. So one way that you can define a graph in Maple is with a matrix, and in this case we have a matrix of weights, um, and so this is how we uh, define a graph this way. And one thing we might want to do is to draw this graph. Um, Often we use the draw graph command for that, but in this case I chose to use the draw network command because it shows it chooses a good layout for these types of flow problem graphs, and um, so that's why this would be appropriate. Um, and we can of course compute a flow, and um, we get that back as the numerical value of the maximum flow, which is in this case 4, and uh, a matrix of flows for along each directed edge, along each arc. And yeah, so this is just generally a type of thing that is useful. Is you can talk about how the algorithm works, and how you have an augmenting path and things like that. But it's also useful to just um, get the answer and be able to just show that whether you're teaching or whether it's by your students who are doing homework. Um, so after we've computed uh, this flow, the easiest way to do it is to just use this as a new definition of a graph. And we can now make this part of the visualization by using this style edges by property command, and then issuing that draw network command again. So now we can easily see, actually, let me uh, display both of these next to each other. I think that was N, yeah. So this way we can easily see the capacity for each edge, and next to it, what the flow is in this particular realization of the max flow. And yeah, I think that can be really helpful to use these types of visualizations. If we're talking about more the study of graphs as objects in themselves, one thing you'd be likely to encounter and to talk to your students about is colorings. So I wanted to show a little bit of what you might use in that subject. So to show this, we start with a graph that is one of those special graphs, the predefined graphs. This is a parameterized one. The flower snarks are a family of graphs with a parameter. This one looks like this. So one thing we can do is just ask for the chromatic number, which in this case is 3. That's of course NP complete computation. Are for the types of graphs that you'd want to actually show in a lecture, that won't be a problem. It's pretty quick for that. But our algorithms are pretty decent for bigger graphs as well. So the chromatic number command just gives you the chromatic number, but it can also give you a coloring that realizes that chromatic number. So obviously that doesn't show you that 3 is an upper bound, but it does show you that 3 is, I'm saying that the wrong way around, I think. It gives you a witness, right? So, and then of course we would probably want to show this. So what happens here in this command 1.2.3 is that Maple computes the chromatic number and also the coloring, or a coloring that realizes that, and assigns it to this variable called coloring. And now coloring is assigned this list of lists. Now, in order to actually show that on a graph, we would choose 3 actual colors, and we would say color each of the vertices in those sublists with the given coloring. And then we can use draw graph, and we see that there is no edge that has 2 the same colors, so this is a valid coloring. And we can also see that there is an odd cycle here, so it can't be 2 colorable, so 3 is indeed the correct number. Great. I also wanted to show the edge coloring feature. So we take another one of the predefined graphs, the Shrikande graph, and this one doesn't have as nice of an embedding in the plane, but if you ask for a 3D display, you can still see it reasonably well, especially if you grab and turn, then you can see what the connectivity of the graph is. Again, we use a chromatic index command rather than chromatic number here. I believe you can also call it chromatic edge number or something like that. There is a synonym that we use, but chromatic index, I think, is the more common term, at least, that I've seen. And just like with the chromatic number command, you can ask for a coloring that realizes that. And there we have such a coloring. In order to show this, we have to pick 6 colors. It was too much work to just pick those by hand, so I chose one of our predefined color palettes. And now we apply that coloring to each of those groups of edges. And I also made the edges a bit thicker because you wouldn't be able to see the color very well otherwise. So it's a little bit more work to convince yourself that this is a valid edge coloring than with the vertex coloring we saw before, but it does appear to work. That's what I wanted to say for now about graph theory. We'll return to it at the end. If any of you have any questions about this, then now would be a good time to ask such a question in the Q&A window, or otherwise I'll continue talking about group theory. So I'll mention 3 things in the group theory topic. So the first thing I wanted to talk about, one of the first things you talk about when you talk about group theory is what's the definition of a group. I find one useful thing to do is to give your students a sense of, try and give them a sense of what the various requirements on your operation, your binary operation are. So one thing you can do is just show a Cayley table of a binary operation or a magma, right? That is not associative or that does not have an inverse, and then just look at it and see if you can see that that's the case. That makes it just more visual and more concrete for the students. So we can do that with Maple. We have a package called Magma that deals with all sorts of sets with a binary operation on it. Generally, a magma, the operation is entirely unrestricted. But you can ask for example, all magmas on 4 objects with a particular property. So if we do this, we see that there are 2 groups of order 4, obviously the cyclic group and the Klein 4 group. Then if we look at magmas that have an inverse but aren't necessarily associative, so those are called loops, we see that there's also 2 of those. So that means there aren't any that don't have the group property, right? So if we want to show a magma that is not a group but that does have inverses, we need to go a bit bigger. And it turns out we can find examples of order 6. Okay, so let's pick out some examples. We use that same enumerate command, but we now ask it to output a list. And what it gives is a multiplication matrix. And just looking at this, you can see that this first one is the cyclic group, which means that this one must be S3. So that's maybe the more interesting one. I don't know, visually more appealing. So, okay, so we choose that as our first multiplication matrix. Um, and now we look at the loops, and they all look fine. There's nothing particularly interesting or the like about them. We, I mean, we don't want to use the first one because that's that cyclic group, but any of the other ones would be fine. So we can use the second one. And now for the associative magma without inverses, this is a little trickier. So if we list these, we just list the first five. We see that many of them don't look so interesting. So we see, for example, we see lots of threes here. So clearly, it would be very, very obvious that these are not a group. Maybe we can find one that's a little bit closer to a group in some sense, to to yeah, make it look more interesting. So if we wanted to do that, we create that list of all these things. I ended my statement with a colon here in order to stop Maple from printing those 2000 multiplication tables, the 2000 Cayley tables. And now we remove the invertible ones with an inverse. And we have still 2200 left. So what I did next is to check for each what the frequency is of each of the 6 numbers in this in the multiplication table, and then compute standard deviations for between the frequencies. And in order to make it look interesting, we want to have a relatively low standard deviation between those. So we see that there's some that have a standard deviation of about 2.4, and then for the rest, the standard deviation is greater than 3. So we can select those multiplication tables where that standard deviation is less than 3. And then we see that there is only 4 of those. And we can look at this manually and see that, well, this one has one row that's all 2s, and this one has a row that's all 2s, and this one has a column that's all 4s. But this one looks interesting, so let's choose that one. And now that we've sort of done this work, we can show those 3 Cayley tables. And yeah, so this is the Cayley table of S3. This is the Cayley table of that magma that is a loop, so it is not associative. In this case, not associative, not just not necessarily, but a non-associative loop. And this one is the one that is associative but not invertible. So you can immediately see that even though we sort of carefully chose the magma to be as interesting looking and as group-like, if you will, as we could, we can see immediately that this is not going to be a group because, yeah, the rows and columns are not permutations. And I don't know if there is a hard truth underneath this, but to my mind, this reflects a little bit the idea that if you have an operation and you want to show that it's a group, then generally it's more work to show that it's associative than to show that there's an inverse. Yeah, I think that you can show that like this. So to recap, I think what I would propose is that if you're doing something like this in your preparation for your lecture, you could spend a little bit of time looking for these Cayley tables, and if you're looking for this sort of thing, and then just show this during the lecture. Okay, we've talked about Cayley tables. Next item I want to discuss is Cayley graphs. I guess I could have sold this as also being on the intersection of graph theory and group theory, but really there isn't any graph theory that I would propose to do with this. So I present it under group theory now. Okay, so now we're truly dealing with group theory, so I'm loading the group theory package, and yeah, so this is just a nice way that you can show something about a group. Basically, show how the generators multiply with the elements, and yeah, gives you a bit of a sense, as you all know, if you teach group theory. Yeah, I just think especially for smaller groups, this is a nice way to visualize what a particular group looks like, what's going on inside it, and we have functionality for that. This also is a nice way to show off how we support the sort of most of the sort of textbook notation for presentations. So this is a presentation for the alternating group on 4 elements, and we can show its Cayley graph with this command here. In this case, again, I figured I would show it as a 3D object. It's just a little bit easier to see that way rather than if you have a static 2D embedding of this. Of course, you could also define A4 as just Alt4, and you get different generators, so you get a different graph, but the same group. So that's maybe also a useful thing to show. Yeah, I'll continue with a slightly more advanced topic that would come later in a course, I think. There are many cases where you might want to talk about, or there's much you can see about a group if you study its lattice of subgroups under inclusion. And that's also something where we spend some time coming up with nice visualizations. I wanted to illustrate that using this quasi-dihedral group, which is a group of order 16. So the sort of most bare bones way to show the subgroup lattice is like this. So what you see is, so here we have the trivial subgroup, and there we have the whole group, and in each layer you have a bunch of subgroups that are grouped by conjugacy class. So in sort of these prime cyclic subgroups, there's 4 that are conjugate to each other, and there's 1 that is different, a different conjugacy class. We can see that even more clearly if we leave out these options to turn off some of the features, because now we'll be able to see, first of all normal subgroups, which are shown highlighted in green. That's of course the same as all subgroups that don't have any other groups in their own conjugacy class and definition, and also the center. So the center is this group, subgroup highlighted in blue, which is of course also a normal subgroup. If you want to show or highlight a particular set of subgroups, you can do that as well. So here we take a look at the particular set of generators that's currently selected for this group. This is a permutation. It's implemented as a permutation group, as you can see. And here's how we can show which where these generators live. So this is the subgroup generated by one of the generators, obviously an element of order 2, and here is an element of order 8. Yeah, that's the one of order 8, and that's the one of order 2, of course. That generates the cyclic subgroup here. And then there's also a notion of subgroup series. You might not discuss this in a first group theory course, but like lower central series or a Fratini series, or there's a bunch of series that are defined in Maple for. I think we can compute them only for permutation groups, but then you can always compute a permutation representation of any group, so it's not really a restriction. And yeah, you can highlight you can highlight those as well. So the objects themselves, also are useful to look at. So we can see that this is a series with 1, 2, 3, 4 members, and we can highlight them because they're of course all subgroups. We can highlight them like this. Let's see these 4. Yeah, once again, if there are any questions, I'd be happy to answer those. And if not, we'll just continue with the last item that I have prepared in this worksheet, which is about graph isomorphism. So this is probably something you could discuss in either a graph theory course or a group theory course. Yeah, there's various things you might want to do with it. One is to just introduce the concept. You can look at just visualizations. So everybody's favorite graph is the Peterson graph. And if we compare that to the dodecahedron graph, it's immediately obvious that they have different numbers of vertices and edges, so they're not isomorphic. But it turns out that there's something we can do to the dodecahedron graph to obtain an isomorphic copy of the Peterson graph. And so that gives a nice example to walk through with your students. And what we do with that is we take the pairs of antipodal points at distance 5 in the dodecahedron graph, and we identify them, and we sort of divide out that relationship, and then we look at the graph we receive then. Okay, so first let's figure out which are all the pairs at distance 5. So we take the distance matrix and we find the pairs at distance 5. So 1 is at distance 5 from 18. And so we see that reflected here in this first pair. And now what we can do is use the contract subgraph command. So what that does is it takes these vertices number 1 and 18, and it identifies them. Any neighbors that of 1 are neighbors of this new vertex, and all neighbors of 18 are also neighbors of this new vertex, right? So okay, so if we do that for each of those pairs, then we now get a graph that doesn't have an obvious layout. That's pretty. I guess we can ask it to do a spring layout. So it looks a little bit better, but still not great. And also you can't see what's going on behind here, so it's maybe better without. But yeah, this is of course at this point an interesting question to ask your students, like how would you know if this is an isomorphism, if this graph is isomorphic to gamma 1? So we display both graphs next to each other. Then it's not obvious that you know that isomorphism is there, and it would of course be especially hard to show non-isomorphism unless you happen to come across an invariant that you can see differs between the two. Like we saw at first, the number of vertices or the number of edges as the most obvious ones, but you know the degree sequence or the spectrum or anything like that, which you could all compute in Maple. I guess that might be an interesting exercise here. To degree sequence, yes, we do. Degree sequence. One degree sequence. Two. So I mean, yeah, we could see that in this case pretty clearly that they're both regular of degree 3. And similarly, we could look at the spectrum and you know see that they're the same, but you know that's not a proof. And a proof that they are the same. What you can do is just try and figure out a permutation of the vertices that maps the one to the other. So of course we have a command for that. In this case, they are isomorphic, and now phi is this mapping that maps the vertices of gamma 2 to the vertices of gamma 1, or I should say the positions of these vertices. And in order to visualize this, I wanted to make an animation. I figured that would be nice. So we can get the current default vertex positions for each of our graphs. So we do that for gamma 1 here. And for gamma 2 here, I scaled and moved it a little bit because for gamma 1, the numbers were between -1 and 1, and for gamma 2, it was between 0 and 1. So in order to make that animation look a bit better, I take that matrix and I multiply it by 2 to make it between 0 and 2, and then I subtract 1 from each entry. So this tilde is an element-wise subtraction. Subtracts 1 from every entry. And now we create 11 different plots. We take this position matrix and this position matrix and interpolate linearly between them. And we set that as the vertex positions for gamma 2 and then create that drawing. And we add that to the sequence here. So we do that, then we get 11 plots, and we ask Maple to display those in sequence. And now here we have an animation, so we can now see that indeed they move from one to the other. So I think this would give a nice overview of the sort of things to think about if you think about graph isomorphism and yeah, what sort of goes into that. We have about 20 minutes left, so I'll ask once again if there are any questions. I have one more section that I can talk about that I prepared. If there are not. So I don't see any questions right now, so I'll just switch to my other worksheet here, which talks about cycles. I'll zoom in a little bit to make it a bit bigger. I think this is about the level of magnification I was in the other worksheet. Let me just remove the output. And make sure that I start in a new session. So I'll want to load the graph theory package. And I'll also want to use the special graphs package. And yeah, so I wanted to talk a little bit about Hamiltonian and Eulerian cycles. So if we talk about these things, it can be tricky for students to keep them apart, I guess. So it's useful if we have an example of a graph that's Hamiltonian but not Eulerian and the opposite, and then to just look at it and see what we see. So these are examples of that. We have the complete bipartite graph on 2 and 4 vertices, and this graph happens to be called the Vrucht graph. I think it's named after a person. And now we can ask Maple to find an Eulerian cycle and in one. And oh, I guess I should first check is which of these are Hamiltonian. So it turns out that I mean, you can see pretty easily that K24 is not Hamiltonian, right? Because once you leave vertex 1, you can only come back there once you've visited all the others, and you can only get to the others by going back and forth between 2 and them, and that's not going to work. For this one, it's a little bit less obvious that it's Hamiltonian, but you could probably figure out a tour with a little bit of puzzling. actually probably makes sense to renumber the vertices because I think going in order of the numbering works in this case. Yeah. Anyway, on the other hand, if we look at the property of being Eulerian, it's the opposite. So G1 is connected, and every vertex has even degree, so it's Eulerian. And the Frucht graph is regular of degree 3, so it's not Eulerian. So we can show the highlighted trail through the Frucht graph through G2, that is the Hamiltonian cycle, and convince ourselves that this is a valid Hamiltonian cycle. It's not so obvious how you would show an Eulerian cycle. I guess you can make another animation. I won't do that right now, but you could just go through these edges and first highlight the first one, and then create a plot, highlight the second one, create another plot, etc. The same way I did in the original worksheet with the isomorphism, showing the isomorphism of the two graphs.